Alright, hello everybody. My name is Germán Garcia. Welcome to another lecture of Applied Matrix Analysis. Today we're discussing the continuation of the least square methods, nonlinear regression, as well as certain applications for this method, and how to calculate some sort of pseudo-inverse of a matrix and the use it's going to give us. So in the previous lecture we have discussed linear regression as using converting our data into a linear problem in which we can get the coefficients of the proper function, the proper best fitting function, out of the matrix that contains the data. And today we're going to do the same by trying to linearize problems with functions that are not linear in terms of its coefficients. We'll see how that works. After that, we'll be discussing recursive least squares and iterative reweighted least squares, which are methods in which we already have least squares method approximation of a function for a certain set of data, and what we want to do is to expand that set of data and assign different weights. So for example, the new function approximates the old data but using different weights. Now, the idea with linear regression is that the models we're working with are linear functions in terms of its coefficient. If you have a cosine x plus b sine x plus c tangent of x, for instance, that's a linear function instead in terms of a, b, and c. That's the difference between linear and nonlinear regression. In this case, we'll be discussing nonlinear functions with respect to the parameters that we want to estimate. Now we're going to consider a nonlinear function of n variables, x1 to xm, defined by a set of parameters r1 to rk, and that we will denote by f of xr, or only f of x, if there is no confusion regarding r. So we're going to assume we have a set of values s, xy, yi, xi, yi, from n-side sample, and we have, as we know, a corresponding system of equations where x is the data, is the equations as we try to approximate to a function. We know we have the following residual vector, given in this way. We know they may be collinear or coplanar, or in this case, if we go for the nonlinear thing, they could be, the points could be on a curve, they could be on a surface, which is generalized version of plane, and what we are going to find more commonly is that they are close to a curve, but not on a curve, and close to a surface, but not on a surface. So what we want to do, again, is to find the curve or the surface that minimizes the distance to the points. Now, finding these coefficients is usually a much more complicated task. It usually requires a numerical method to minimize this norm. Have a very nice example in Marquardt-Levenburg method, which is also known as damped least squares. There might be a project topic involving this that will probably be one of the interesting ones in case you want to check that. But now, by using the proper changes of variable and function, certain models can be rewritten using certain functions g sub I. In this case, if we manage to perform a change of variable and function that makes the function we want to approximate a linear function, then we can use least squares method to approximate it. So now I'm going to show you some very nice examples of this phenomenon. The most common are exponentials, powers, monomial times exponential, or for example, the sign of a polynomial, sign of r1 plus r2x plus r3x squared. All those are non-linear functions, but using some methods we can linearize them. For the first example, we're going to see the exponential model. This is definitely one of the most important. The trick we do here is we take logarithms. So we define any function as the logarithm of f, and we call it f of L. And what we have is when we calculate this logarithm has this property that it turns products into sums and powers into products. And so we take the logarithm of this, we get logarithm of R1 plus R2x, and now we have a linear function in terms of this logarithm and in terms of x. So we can describe this as q plus R2x, and this is already a linear function, which means we can apply least square method with this data, but we have to include this column in our considerations, as we will see. Now we're going to try to use this exponential model to find a good least square fit with these data points. Now, using the theory that we have just seen, we can describe this linearized function, the L here is for linearized, as q plus R2x, and remember here that what we want to estimate is q and R2, because once we have a value of q, we can turn back to this, and we'll have R1 is the exponential of q. So we create a new column with our linearized function, and in this case, f linearized of 0 is 1 times q plus 0 times R2, and we get this, and same with the rest of the data, and we get this column, and so we can arm our linear squares problem. We have matrix A, we have a vector of things we want to estimate, and we have the vector y. So we calculate the normal equations for this. We have this beautiful thing over here, and this thing over here, and once we solve it, we get q is equal to this number over here, and R2 can be estimated as this. Now, the problem is not done yet. We have to guess R1 using the value of q. So we put in our equation q equal to natural logarithm of R1, and we get coefficient R1 as e to the power of q, which is roughly 1.58. And so when we put it back into the model, we have the best exponential model to fit this data in terms of minimizing norm 2 of the error vector is this function over here. Now, how well does this fit the points? Well, the points are not exactly on the curve, but they are considerably close. So we can say that this is really a good fitting. Now, the next interesting one is the power law model, in which what we want to estimate is R1 and R2 here. We're going to use the same trick, applying a natural logarithm. So our linearized function is the logarithm of this function, which is logarithm of R1 plus R2 logarithm of x. This is really important here, because here it's not enough that we use a change of function, we also have to do a change of variable. In this case, we call natural logarithm of x equal t, and now we have this linearized function of x, which is q plus R2 times t. Now, this is a linear model in terms of t, of course. So, for example, let's use the mean, height, and weights of boys from ages 2 to 11, which were collected in a survey done by the CDC in 2002. And we're going to see how we can fit this with a power law model. We start with our model. We do the linearization, where t is the natural logarithm of x. And what we get is this thing over here. But remember, we have to calculate t and we have to calculate x. And now when we use vector x, this is not taken anymore, but this is what matters. Now, we will obtain a determined system of equations that can be written in this form. And once we do the normal equations for this, we get q equal to 2.79 and R2 is 2.42. Now that we have both estimates, we remember q is natural logarithm of R1, and so R1 is equal q, which is a bit more than 16. So our best power model is 1.633 x to the power of 2.42. Now, how well does this fit the data? Pretty well. In this case, what we are doing is not assume the exponent, but try to calculate it instead. Now we can go one step further and mix both. We're going to see what happens with the model R1 x e power R2x. We use the same trick again, but in this case, what they have here is we have the natural logarithm of x that we have to move to the other side. And what we get is that the logarithm of f of x minus logarithm of x is our old friend q plus R2x. So we call our linearized function this, logarithm of f minus logarithm of x, and that's what we calculate with. And with this now we can apply the least square method. Now we're going to try to force this method into meet this table of data. Sorry, and in this case we calculate logarithm of f of x, which is this one here, minus logarithm of x, and we have these numbers over here. I haven't put them in decimals because it's really not relevant, and it's more interesting that you see that this is logarithm of this column minus logarithm of this other column. So you see how this is calculated and operated with. Now we obtain an overdetermined system of equations again, which we can write in this form using the least square method. Now the normal equations here that we will use give this result. And finally we recover R1 by doing e to the power of q. And we get 9.77 times x times e to this power here, which is it's an inverse exponential. And this is how the model fits the data. Now this is pretty good. And it's probably much more precise than if we had asked for an instance, a parabola or something like that. In this case, this type of mixed monomial and exponential models are pretty common because they have really interesting flexion properties. Now, what do we do with this sign of a polynomial? The sign of a polynomial is something that may look intimidating at in the first place, but what we are going to do is to use the arc sign. The arc sign of f of x is the argument of the sign, and this is a linear function in terms of the coefficients R1, R2, R3, and so we call our linearized function arc sign of f of x. And now we have the problem has turned into calculating the proper column and fitting it to a parabola. Now, I don't think an example of this one because you may actually be bored of approximating things to parabolas. However, one thing that is actually more interesting is that if we have already approximated a certain set of data using the least squares method or weighted least squares or anything like that, we may want to expand the data set without repeating all the calculations, which could actually be quite time consuming. I mean, comparing to just extending the data set as we are going to see how it's done, redoing the whole least squares is computationally more costly. So we're going to see how this works. This we will usually combine it with weights, as we have mentioned before, because we may want or we may find data that we think are more relevant than the old ones, and so we can assign small weights to the old data and big weights to the new data, so the model fits better once in detriment of the others. So it gives the model a bit more of adaptability over time. In this case, we're going to remember or to show, in case you haven't seen this before, here A is an n times n matrix, U is n times k, C is k times k, and V is k times n. So this is an n times n matrix. And what this matrix inversion lemma says is that the inverse of A plus UCV to the power of minus 1 is calculated in this way. Now this looks a bit bulky, but the easiest way to prove this is if you multiply both and smack them against one another, everything is going to cancel. You use the distributive property of the matrix product with respect to sum, and what you get is that everything is going to cancel, and in the end what you have is basically 1. So it's proved. This type of inverse of matrices is always solved in the same way. If you want to see that something is the inverse of something else, you multiply both. If you get 1, it's true that they're inverses. If it's not 1, or the identity in the corresponding dimension in this case, then it's not. Now we're going to work with a slightly simpler one. If we have B and B transposed, so the role of C is played by the corresponding identity here. We have this slightly less bulky lemma over here that will help you now. So consider that we have solved this least squares problem with a data set of size n-1, and we want to expand our data. We have an extra observation. This transpose goes here. And so we want to add it. I mean, what is the solution to the least squares problem by using n entries instead of n-1? Now we're going to let this matrix here be equal to an transposed an inverse, and using the inversion lemma, what we have here is that xn is equal to this little monster over here. Now, what is interesting about this inverse element that appears here? So we can divide by it. If we only have one observation, this is a number. You know, this identity is a 1, so this is a number, and so we can divide by that. If we let this coefficient be called kn, this is exactly equal to pn an, and so what we have in the end is pn minus 1 minus this little monster over here times this little monster over here. Now, this may look a little bulky, but we are going to smash it into our equation and see how it works. So we have xn equals pn, which remember is this matrix over here, times a transpose n minus 1, y minus 1 plus an yn is equal to pn a transpose n minus 1, yn minus 1 plus kn yn, with kn again being this thing over here. We omit this bracket because it doesn't belong here, and what we have here, is that xn depends on x minus 1, this coefficient that is easy to calculate, our vector y, and this interesting product here. This is not a vector y. This is the observation y, and this product of vector transpose times vector. So, namely, if we get a new observation, we can calculate using these formulas. This is what is called an iterative method. You can expand one step ahead at every moment if you just define this coefficient over here and this pn over here, because pn minus 1 is known. And with this you can calculate vector x going from vector xn minus 1. Remember, this is known, this isn't known, but this is known. And so, the most usual way to use this is using exponential weights in the observations, which means we are going to slowly be forgetting the first measurements. If we give it a forgetting factor lambda, the iterations, here we put a lambda, the iterations become something like this. We put k sub n in this way, pn in this way with lambda minus 1 here and lambda minus 1 here. And what we get in the end is this same formula, but it has this lambda here playing some role. Now, take a look to reflect upon this. We are using the results of the least square method with n-1 observations. We have it here, and we have it here, and we have it here. And what we are doing with it is building something that is one dimension larger. That's the key point of it. Now, if you want to add a bunch of observations instead, we can't set this to divide because this is not a scalar anymore. If we go to the definition again, this thing here, if we are adding more than one observation, then this is a 2 times 2 matrix. So instead of dividing, we have to calculate this matrix and invert it, but the model works in the exact same way. Now, K of n is generally called gain factor, and while the calculations to get the iteration formula is pretty complicated, really, I mean, this may look extremely bulky. In the end, most of the times you hand it to a computer and let the computer do it. So the main virtue of this is that it's really easy to program, as all iterative methods are. The idea is, we decompose a solution into parts. We have the solution for a part of it, and we introduce a correction that's derived from the new data, and we use the old solution to save up a lot of time on calculations, really. Now, I'm going to show you what iterative reweighted least squares means. And that is, we're going to iteratively apply weighted least square solutions in order to lower the impact of outliers in the data. Okay, the idea here is that if we use weighted least squares, it's generally because we want to handle outliers properly. And so we're going to go through the following steps. We calculate ordinary least squares. Then, based on the residuals that we get, we calculate the proper weights for each observation. We solve the weighted least squares problem with the calculated weights. And what we do now is alternate these steps, like recalculate based on the residuals and solve the problem again until the weights converge. What does converge mean? That they stop changing. Like, if you do one step and get the same weights that you had in the previous step, we are done, we are closed, and those are the proper weights to handle outliers. This is a really interesting one. Like, there is sometimes you assign weights randomly, but you don't really have to. You can use this method instead. Now, weight function is usually chosen among one of these. Namely, we use a power of the error here, the norm of the observation y, to the power of p minus 2, but this is only if we're working with norm p. Otherwise, you'll probably use bi-square function, wy equals 0 if the r of y is greater than 1, and otherwise we give it like this. This is going to be always between 0 and 1, because this is between 0 and 1 in itself. And another option is the Welsh weight function, which is exponential of minus ri squared. In all cases, ri is the residual point I, and this function ri is calculated in this way. Now there is a lot of notation. There is a lot of notation here. T is a tuning parameter. S is the median absolute deviation of the residuals from the median, excluding the p smallest values, where p is the number of columns of A, divided by this, which is an estimate that is already calculated. And h of I is the ith diagonal element of this matrix over here. Now, our function is really complicated now that I stop thinking. So, iterative reweighted least squares is usually called robust estimation, or there is a lot of MATLAB packages that call it robust estimation at least. We will only use it when we have the conscience that we have outliers in our data. Like we have several points that go wherever they want instead of where they should. We will use it to kind of flatten them out. Now, if it's not necessary, I would rather you not use it, because computationally speaking, it's more costly, it's more expensive than ordinary least squares method. And usually, if you're working with small data sets, you can see with your naked eye how if there's outliers and how they behave, and so you can choose proper weights. Now, choosing a correct weight function and tuning parameter can be tricky, but often doesn't matter too much as long as it somehow matches the type of behavior we are looking for. For example, we can define our weight function point by point, which in the case of being working with a small data set is pretty adequate, because it allows you to somehow fine-tune the points a little bit better. Of course, if we're working with large data set, that's not possible, and then we have to go to one of these functions here. By square is pretty interesting, by the way. And so really, one thing that is always nice to check is you can use a couple of them. You can use different wave functions, and the one that matches most, that fits best the model, is the one you use, and you discard the other one. That's a possible strategy. Now, this is it for iterative reweighted least squares. It's a really interesting problem for those of you who want to dig a bit deeper into it. And now I'm going to mention a last type of, some last types of least square methods. We won't use them, but they're there, and it's good for you to know. First one, non-negative least squares. This is related to linear programming, and we are requiring all estimated parameters to be non-negative. Of course, as you can imagine, this can actually lead to certain difficulties at the end of doing these calculations, certain restrictions, and all that. But there's different iterative methods that converge to nice solutions. So that's that. Another one is constrained least squares. It's a bit more general than non-negative, but instead of requiring all coefficients to be positive, we put other constraints. This is interesting because it's not only more flexible than non-negative least squares, it's also more general. Like in methods that are used to calculate these constrained least square problems can be used in non-negative least squares problems, as non-negative is a constraint itself. I don't know if that is the word, but yeah. Now, another common way to get more reliable estimates, if there are outliers, that are there are some regularization methods. There is lasso method, there is a rich regression, but that's something for another day. For now, this was it from this lecture. Thank you very much for joining.